In this video, I'm going to go over the ideal gas problems that are in your notes packet, starting on page 17, starting with this first you-do problem. So, number 1. A gas mixture at 20 degrees Celsius, so T equals 20 Celsius, and 2 atm, and this is a mixture, and so if I'm giving you the pressure of the mixture, that is the P total, or P tot, 2 atm, contains 4.4 moles of hydrogen, so NH2 equals 0.40 moles, 0.15 moles of O2, 0.15 moles, and 0.5 moles of nitrogen. Assuming ideal gas, what's the partial pressure of hydrogen in the mixture? So we're looking for the pressure of hydrogen. So when I look at this problem, hopefully if you look at this, you see we have moles of different substances, we have pressure. This is going to be something to do with Dalton's law, but we don't know the pressure of any of these gases. And I hope you would go to your formula chart, your AP formula chart, and start looking at your equations, and hopefully you'll see that you have the equation that's pressure of a gas, so pressure of hydrogen can equal the total pressure times the mole fraction of hydrogen. Now, we don't have the mole fraction of hydrogen, but we can figure that out because our formula chart also tells us that the mole fraction of hydrogen equals the mole fraction of hydrogen over the total moles. Now, I gave you how many moles there were of each gas. So, in total, our total moles is you just add them up, 0.4 plus 0.15 plus 0.5. So our mole total is 0.4 plus, and that's 0.5, not 0.05. So our total moles is 1.05. So I'm going to plug that into my mole fraction equation first. So the mole fraction of hydrogen equals, so I'm looking for, I know how many moles of hydrogen there are, so 0.4 moles over the total moles, 1.05. And my mole fraction of hydrogen is 0.38. Now I can plug into this equation. So pressure of hydrogen equals the total pressure 2 times the mole fraction of hydrogen, which is 0.38. Multiply those numbers, and the pressure of hydrogen in this gas is 0.76 atm. And that would be your answer. Now you should check, okay, the total pressure is 2 atm, so that is okay. The hydrogen's pressure is 0.6. The pressure of an individual gas should never be greater than the total pressure. Also, let's look at our gases, H2, O2, N2. Hydrogen is 0.4 of the 1.5, so it's less than half of the moles of gas, so it should not be half of the total pressure. It should be a little less than half of the total pressure, which it is, 0.76. Okay. Number 2. 193 milliliters of oxygen were collected. So V of O2, 193 milliliters. And it was collected over water on a day when the atmospheric pressure, is 762 millimeters of mercury. The temperature of water was TH2O, 23 degrees Celsius. Oops. Be nice if I could write the number. And then the vapor pressure of water is 21.1 millimeters of mercury. So part A, what's the pressure of the oxygen gas collected? So whenever you collect a gas over water, you have to take the total pressure, or the pressure of the atmosphere. That's the same thing. and subtract the pressure of the water vapor from it, and that will give you the pressure of your gas. So 762 minus 21.1, and that is 740.9 millimeters of mercury. That's the pressure of my gas. You have to subtract the pressure of the water from the atmospheric for the total pressure. B, how many moles of oxygen were created? Okay, so I know my volume of oxygen is 193 milliliters, which is 0.193 liters. My pressure of oxygen is 740.9 millimeters of mercury. And let's go ahead and change that to ATM because you're going to have to anyway. 760 millimeters of mercury, 1 ATM. That is 0.975 ATM. I'm looking for moles. I don't know that. I do know the temperature was 23 degrees Celsius, which add 273 to get it to Kelvin, 296 K. And so how are we going to figure out how many moles we have? Which equation are we going to use? We have V, we have P, we're looking for N. So we're going to use we have T. We're going to use our ideal gas law. PV equals nRT. Okay, so the pressure, 0.975 times the volume, 0.193 equals, I don't know, N, my R, 0.08206 times my T, 296. Multiply out. .188175 equals N times 24.28976, and then to solve for N, I'm going to have to divide each side by that 24 number. And we get N equals 0.00775 moles of O2. And then for part C, part C was how many grams of oxygen were collected. So if I have 0.00775 moles of O2 and I want to change that to grams, I just need to do a simple mole to gram conversion. Now remember it's O2, so 1 mole of O2 has 32 grams, not 16. You have to multiply the molar mass by 2 because there are 2 oxygens, and that is 0.248 grams of O2 collected. Number 3, an ideal gas sample has a mass equals 1.28 grams. The volume is 0.500 liters. The temperature is 127 degrees Celsius, and the pressure is 2 ATM. What is the molar mass of the gas? So molar mass I've been abbreviating as MM. Makes my life easier. Really fast. Let's change that temperature because we don't ever use temperature in Celsius, and that's 400 Kelvin. Okay, so we're talking about one gas. The gas is not changing, so I'm not using the combined gas law. You know, it's not like getting a new pressure or anything. And so if we think about our ideal gas law, your formula chart shows you this. PV equals nRT. Your formula chart also shows you N equals mass over molar mass. And so instead of having N in this equation, I'm going to substitute it for this. And remember, your formula chart gives you this, so that's nothing you have to memorize. And now, for simplicity's sake, I'm going to do mass as M, molar mass as MM. Your formula chart has it like molar mass bold, but I can't really do bold on a video. Okay, So pressure. So that makes that equation now. PV equals M over MM times RT. And then we just need to plug in and solve for molar mass. So 2 ATM times the volume, 0.5, equals mass, I know, 1.28 over the molar mass times R, 0.08206 times T. So 1 equals 1.28 over MM times, oh, my temperature, I know my temperature, I don't know why I wrote T, it's 400 K. So 0.08206 times 400 is 32.824. Now I'm trying to solve for MM, so let's go ahead and divide each side. Let's get rid of this, so divide each side by the 32.842. Now I have 0.0305 equals 1.28 over MM. Now algebraically, you, I hope, know, flip it around, or if you don't know, you can't remember, go old school. We need to solve for MM, so multiply MM on both sides. That cancels out. Now I have the molar mass times 0.0305 equals 1.28. Divide each side by 0.0305, and we get that the molar mass equals 41.97, and it's molar mass, so the unit is grams per mole. And it should have 3 sig figs, so 42.0 would be the better answer. There's number 3. Number 4. Given the following reaction, 2NO plus O2 makes 2NO2. How many liters of gaseous oxygen, so I'm looking for the volume of O2, are needed to produce 6.5 liters of gaseous nitrogen dioxide? So my volume of NO2 is 6.50 liters, and both gases are at STP. So when gases are at STP, 1 mole of any gas equals 22.4 liters. That is true. Now you could do this as an ideal gas, but you don't have to because it's at STP. This conversion is true. And so all we actually have to do is, okay, let me focus this because that's annoying. Okay, so 6.5 liters of NO2 times 22.4 liters NO2, or in a mole of NO2, times 2 moles NO2. We're solving for oxygen, so that is 1 mole O2, and then 1 mole O2 is 22.4 liters O2. That's all I have to do, some stoic. And you get that it equals 3.25 liters of oxygen. On the next video, I'm going to go through 5 through 9 of this page.